I'm Alvin. I'm a graduate student and I study programming languages at the University of Waterloo. For the last year, I've been studying how to add module systems to the C programming language, though this work also applies to other low-level systems programming languages. This is a re-recording of a talk that I've given for the ONPLS 2026 seminar. Let's first start by looking at C++ 20 modules. I find them interesting because they do not allow cyclic imports. So if we look at the example on the left-hand side, struct node and struct edge depend on each other. If we migrate this code to C++ 20 modules, then both structs must be merged into the same module. Note that this isn't necessarily a bad thing, as this restriction can help with code readability, compile times, and static initialization order. But it does catch a number of people out, myself included, if you expected that C++ 20 modules are a replacement for header files. So that's what I want to achieve here in this project. Create a module system that handles cyclic imports so it can serve as a replacement for header files. The first challenge we run into is handling the context sensitivity of C. In the example on the right, A star B could be interpreted as either multiplication or declaring a variable B of type pointer to A. Well, actually, this case is not ambiguous because expressions are not allowed at file scope. It just so happens that C is not context sensitive outside of expressions, so we can extract file scope symbol names without needing a symbol table. Then we can use this information to build a symbol table to parse the context sensitive parts of the file with. That said, I put a star because other languages still have context sensitivity issues at file scope, which need to be dealt with. For example, we run into issues with C++ because of its template syntax. So we combine the file scope symbol names of the imports with the existing file to create a symbol table, which allows us to parse the rest of the file. Here, other module should export a typedef for A, but C could be a typedef or a variable. Another detail is that other module could define its own struct S as long as it doesn't export it, because then it would conflict with struct S in module example. Once that's set up, we still have another problem. If I import module M, then I should be able to access a.b.c, because A has field B, whose type has field C. The compiler needs to know all of these details, so the dependency tracing step essentially functions like a dynamic preprocessor to stitch together all the necessary information to give to the compiler. Looking at it at a high level, each of these file columns represents a module, and we first perform interface generation on each of them in parallel, followed by scope resolution and dependency tracing. This results in a .c file which we can send off to the C compiler to compile into machine code. Now, let's look at this from the user perspective. A module file starts with a module identifier, and then you have a bunch of imports. It's very similar to how C++ 20 modules are set up, but with a caveat. Everything must be a symbol definition, so no forward declarations or function prototypes or a forward declaration of a struct. This is because all file scope symbols within a module are already visible to each other, so having those declarations only adds clutter. For clarity, if you want to export a symbol, export must be the first keyword. Note that the module system runs after the preprocessor, so you lose the ability to export macros, but in return, you eliminate the possibility of a macro performing arbitrary text manipulation. This allows us to guarantee that imports are order independent. Let's demonstrate with an example. While I do that, I want to advertise that the module system was specifically designed so each module has an equivalent representation as a bunch of .h files and .c files. Now, I put a star here because some constructs like pointer types are a bit tricky, but for the most part, it's a straightforward translation. Basically, each module file has its own .c file, and each symbol has two .h files, one for its declaration and one for its definition. On the right-hand side, we have 3 module files. On the left, we have the equivalent .h/.c representation. We see the 3 .c files, one for each module file, and we see 3 .h files, one for each declaration of the 3 symbols. Then on the next slide, we have 3 .h files, one for each definition of the 3 symbols. So we're taking the work of manually managing dependencies between symbols off of the programmer's plate. That gives you more time to focus on the actual functionality. By the way, if you're interested in poking around, we have an implementation for you to poke around in. It's only for a simplified subset of C, but it can handle all of the code in the slides. Additionally, we have one in the works that will support C99, so that's really cool. Just like the previous example, it treats symbol uses as either needs declaration or needs definition. And one of the key features you can do with it right now is import inline functions. So let's suppose you want to test out whether making a certain function inline improves performance. With header files, you'd have to pull the definition into a .h file, then handle any missing header files. That's a lot of work for a simple experiment. But with C modules, all you have to do is write inline on the function definition, and the module system will handle the rest. Another interesting detail is that the implementation treats expressions as token streams instead of being parsed. The idea is that you do a symbol table lookup for every identifier, ignoring cases where the identifier is not in the symbol table. This works because you need to write out the name of a symbol in order to use it, so the algorithm is overestimating symbol dependencies. Of course, a future iteration should parse the expressions properly in order to get proper error diagnostics, but this is a quick and easy way of getting the functionality working. The simplicity of this module system allows us to extend it in many ways. I've listed 6 here, but there are more ways to extend the module system. First off, one limitation of the current setup is that a C module cannot import a header file. C++20 offers 2 options. You could import header.h like the other imports, or you could #include header.h in the global module fragment. Second, we have export-import. This works like syntactic sugar, so you can import multiple modules with a single import statement. And it works because imports are order independent. Third, we have module namespacing. You see, I lied a bit when I was talking about scope resolution. So on this slide, if other module defines its own struct S and dependency tracing causes it to be in the C code sent to the compiler, then you'll get a name conflict. Module namespacing would fix this issue by avoiding intermodule name conflicts. Fourth, we have import as module name. Right now, imports are essentially a wildcard import because that's how it's done in C right now. This feature would allow the module system to be a little bit more careful with namespace pollution. Fifth, we have tagged exports. Here's a use case. Imagine you have a threading library and you want to expose some functions to the garbage collection library, but not to the other importers. This functionality would allow you to tag exports so only the garbage collector gets it. Finally, we have dependency files. You can think of it as the .d files that preprocessors emit. That being said, having a module system opens up a bigger opportunity to create a language-specific build system, which would give us more fine-grained incremental compilation. And the rabbit hole keeps getting deeper. For one thing, the idea is generalizable to other languages like C++ or C for all. That said, you may need a few tricks to be able to extract file-level symbol names. Another area that I didn't discuss here is static initialization order, which has a number of options. Some systems order them at compile time while others order them at runtime, and there are trade-offs to consider there. In terms of optimizations, you could create a language-specific build system for better compile times or automatically create unitary builds for maximum runtime performance. Having a module system also enables better static analysis opportunities, which is important for developer tooling. And finally, we get to the big thing, which is that our module system is simple enough that automating the migration process is possible, which would enable a huge amount of legacy code to be upgraded overnight. And if you're interested in learning more, these two other links go into more detail, and the implementation is pretty short and self-documenting. All in all, I think there's a lot of untapped potential to improve legacy code bases. So I would like to finish off with a bit of an opinion, which is that there's a lot of hype these days about jumping to the next big shiny language or framework when it could be better to improve existing systems. Now, the kicker is that suppose you wanted to switch a legacy C code base to using, say, Zig. I would argue that it is easier to migrate C module code to Zig than plain C code because the code representation is more similar. So you see, incremental improvements to older languages like C helps everyone. And I hope you are just as excited as I am with these kinds of problems and potential value we can bring here.